Whenever we apply method of maximum likelihood, our usual practice is to assume some underlying probability distributions. In fact, so far we have developed the theory behind the likelihood function and MLE. Always there were some underlying probability distributional assumptions. But life is not always so simple. In many real life cases, it is quite hard and unrealistic to assume some suitable probability model. But maximum likelihood method is so charming and useful that we desire to apply it even in these tough cases also. Through quasi-likelihood method, we can meet this expectation. In this module, we will discuss the quasi-likelihood and its different aspects. In order to construct a likelihood function, the probability distributions of the random sample observations should be specified. But unfortunately, often those probability distributions are not available except few information revealing few aspects of the data like the domain of the sample responses, how the mean or median response is affected by external stimuli or covariates, how variability of the response changes with the average response, whether the observations are statistically independent, whether the response distribution under fixed covariate conditions is symmetric or skewed. But method of likelihood is one of the most elegant method for statistical inference. So we always want to have it for application of statistical inference no matter what the existing situation is. To draw inference about the parameter even based on the insufficient information as above, the likelihood function so constructed is called the quasi-likelihood function. We concentrate mainly on the case where the observations are statistically independent and where the effects of interest can be described by a model for expected response, say mu curl. Obviously, here we assume that the expectation of the response exists. Some common and relaxed assumptions. First assumption. Let the response vector be y curl whose components are y1, y2, yn. The components of the response vectors are independent with expectation of y curl equal to mu curl, where the components of mu curl are mu1, mu2, mun. Obviously, here mu I denotes expectation of ith component of y curl, that is expectation of yi. And dispersion matrix of the vector y curl equal to, say, sigma square into some matrix V of mu curl, where sigma square may be known and V mu curl is a matrix of known functions. That means the functional form of V mu curl should be known. Obviously, V mu curl is a diagonal matrix whose diagonal elements are, say, V1 mu curl, V2 mu curl, etc. up to Vn mu curl. As the components of y curl are independent and automatically covariance between yi and yj equal to 0 for all I not equal to j. In presence of regression, our next assumption is the parameter of interest, say beta curl, relates the dependence of mu curl to covariate vector x curl. That case, the symbol mu curl function of beta curl denotes the regression function depending on x curl. Our next assumption is sigma square is constant at least with respect to beta curl. The final assumption is Vi mu curl should be equal to Vi mu I. That is, it should be dependent only on the ith component of mu curl and not over the other components. As a result, the matrix V mu curl becomes a diagonal matrix whose diagonal elements are now V1 function of mu1, V2 function of mu2, etc., Vn function of mun. Let us consider now the construction of quasi-likelihood function. First, consider the IID observations y1, y2, yn with common mean mu and common variance sigma square v mu. Now consider the function u, which is a function of mu and it is based on the response vector y curl. It is defined as summation I from 1 to n yi minus mu divided by sigma square into v mu. Now, this function u has the following properties. First property, expectation of u equal to 0. Next, variance of u equal to n divided by sigma square times v mu. And third property is expectation of minus del u del mu equal to variance of u. Let us now check these properties. Now expectation of u equal to summation I from 1 to n expectation of yi minus mu divided by sigma square times v mu, and naturally this is equal to summation I from 1 to n mu minus mu divided by sigma square times v mu, because expectation of yi is itself mu. As a result, it is equal to 0. Next, variance of u equal to variance of summation I from 1 to n yi minus mu divided by sigma square times v mu. Now, yi's are independent and all the other terms in this expression are fixed. As a result, it is same as summation I from 1 to n variance of yi divided by sigma to the power 4 times v mu function square. Now this is equal to n times sigma square times v mu divided by sigma to the power 4 times v mu square, because variance of yi is again sigma square times v mu and the cases are IID. So finally we get variance of u equal to n divided by sigma square times v mu. Now, the first order derivative of the function u with respect to mu is equal to v mu times summation I from 1 to n of minus 1 minus v prime mu times summation I from 1 to n yi minus mu whole divided by sigma square times v mu square. Here, v prime mu denotes the first order derivative of the function v mu with respect to mu. Now this implies expectation of minus of del u del mu equal to n times v mu plus v prime mu times summation expectation of yi minus mu whole divided by sigma square times v mu square. Since we know already that expectation of yi is again mu, so as a result it becomes n times v mu plus v prime mu times 0 whole divided by sigma square times v mu square, and finally it gives n by sigma square times v mu, which we have already known that is equal to variance of u. So, we have already checked the fundamental properties of the function u. Now, it is interesting to note that these properties are also true for the score function del L del mu, where L denotes the log likelihood function provided the random responses yi's have a distribution in the exponential family with the form of PMF or PDF as f theta y equal to e to the power y theta minus b theta by some function fi plus some function c of y and phi. This typical family is known as exponential dispersion family. So, here the requirement is yi's should have distribution in exponential dispersion family. Now, in this family, the form of PDF includes the term theta, b theta and phi, where theta denotes canonical parameter, b theta denotes the cumulant function, and phi denotes dispersion parameter. Before we realize this fact, that is, the properties of the function u is also true for the score function, we should know that if y follows PMF or PDF belonging to exponential dispersion family, then mu, that is expectation of y, should be equal to b prime theta and variance of y should be equal to b double prime theta times a phi, where as usual b prime theta and b double prime theta denote the first and second order derivative of the function b theta with respect to theta. Now, before going further, let us verify these two results. We know that integration of PDF f theta y dy is equal to 1. Obviously, here without loss of generality, we have taken that f theta y denotes the PDF. Now, if it were PMF, then integration should be replaced by summation. Anyway, integration of f theta y dy should be equal to 1. This means del theta of this integration is equal to del theta of 1, and that is naturally equal to 0. This implies an implied by integration of del theta f theta y dy equal to 0, provided interchanging of the order of integration and differentiation is permissible, and we know in exponential family it is permissible. Now, this is equivalent to integration of del theta log of f theta y times f theta y dy, and that is equal to 0. Now, this can be stated as nothing but expectation of del theta log of f theta y, and that is equal to 0. Let us denote this expression by, say, star. But here in our case, log of f theta y equal to y theta minus b theta divided by fi plus c of y phi. This implies del theta of log of f theta y equal to y minus b prime theta divided by fi, or expectation of this thing, that is expectation of del theta log of f theta y is equal to expectation of y minus b prime theta divided by fi, and that is equal to mu minus b prime theta by fi, because we already know expectation of y equal to mu. And therefore, from star, we can easily say that this expectation is equal to 0, and as a result, mu equal to b prime theta. Again, del theta of integration del theta log f theta y times f theta y dy is again 0. And once again interchanging the order of integration and differentiation, we get under integration sign del square del theta square of log of f theta y plus del theta of log of f theta y whole square, entire thing multiplied by f theta y times dy, and that is naturally equal to 0. In terms of expectation, this expression naturally becomes expectation of del square del theta square of log of f theta y plus expectation of del theta log of f theta y whole square, and that is equal to 0. Let us denote this expression by, say, double star. Now here del square del theta square of log of f theta y is equal to minus b double prime theta divided by fi, and del theta of log of f theta y whole square is equal to y minus b prime theta whole square divided by fi square. So the expression double star implies minus b double prime theta by fi plus expectation of y minus b prime theta whole square by fi square equal to 0. As we know that b prime theta is nothing but mean mu, and expectation of y minus mu whole square is equal to variance of y. So finally we get from this expression that minus b double prime theta by fi plus variance of y by fi square equal to 0. As a result, we get variance of y equal to b double prime theta times fi, and that can be said to be equivalent to some sigma squared times some function v mu. Why it is so? Because we already know that our mu is nothing but b prime theta. That means theta is expressible as a function of mu. And as a result, the second order derivative of theta, that is b double prime theta, is again some another function of mu, and it may be denoted by, say, v mu. Now go back to realizing the fact related to score function del mu of the log likelihood function small l. Now based on a random sample y1, y2, yn of size n, the log likelihood function will be small l of theta, and that is equal to log of f theta y curl, where y curl is the response vector, and that is equal to summation I from 1 to n yi times theta minus b theta whole divided by fi plus summation I from 1 to n c of yi phi. So, like the expression star and double star, in the same way here also we get expectation of del theta of small l equal to 0, and expectation of del theta square of small l plus expectation of del theta of small l whole square, that is again equal to 0. Let us denote these two expressions by O cross and O double cross. Also, the second order derivative of log likelihood function with respect to theta gives minus n times b double prime theta divided by fi, and del mu of theta, which is actually 1 by del mu del theta, that is automatically equal to 1 by b double prime theta, because mu is already b prime theta. Now expectation of del mu of l theta can be expressed as del theta del mu times expectation of del theta of l theta, and that is equal to 0 from the expression O cross. Let us denote this new expression, that is expectation of del mu of l theta, equal to 0 by, say, bullet. Now we have to pass through a stereotype manipulations. To start with this, consider the second order derivative of log likelihood function L theta with respect to mu. That can be expressed as del mu of L theta, and that is equal to del mu of theta times del theta of L theta. So it is basically a chain rule of differentiation. On simplification, it becomes del squared theta del mu squared times del theta of L theta plus del theta del mu times del mu of del theta of L theta. That is again equal to del squared theta del mu squared times del theta of L theta plus del theta of del mu times del theta del mu times del theta square of L theta. Now this is again equal to del squared theta del mu squared times del theta of L theta minus 1 by b double prime theta times 1 by b double prime theta times n b double prime theta by fi. This is natural because del theta del mu equal to 1 by b double prime theta. So finally, taking expectation on minus of del squared del mu square of L theta, we get from this expression that this is equal to n by b double prime theta times fi, because expectation of del theta of L theta equal to 0 by the expression O cross. So this implies expectation of minus del squared del mu square of L theta is equal to n by sigma squared times v mu, and that is nothing but n by variance of y. Let us denote this expression by double bullet. Now, variance of del mu of L theta is equal to expectation of del mu of L theta square minus expectation square of del mu of L theta. Since by bullet we now know that expectation of del mu of L theta equal to 0, so variance of del mu of L theta is simply expectation of del mu of L theta whole square. But from double O cross, we know that expectation of del mu of L theta whole square is actually equal to minus of expectation of del mu square of L theta, and that is equal to expectation of minus of del mu square of L theta. So this implies variance of del mu of L theta is equal to expectation of minus del mu square of L theta, and that is again n by sigma square v mu, which is equal to n by variance of y. Actually, we got this using double bullet. And use this expression to denote triple bullet, that is variance of del mu of L theta equal to n by variance of y is denoted by the expression triple bullet. The expressions under bullet, double bullet and triple bullet now ensure the fact that the function u defined earlier bears the same characteristic features as the characteristics a score function del mu of L reflects in case of an exponential dispersion family member. In other words, the function u can play the role of a score function even when the knowledge about the probability law of the random sample observations is either nil or too insufficient to construct the original score function del mu of small l. Now define q of mu and y curl as summation I from 1 to n integration from yi to mu yi minus t divided by sigma squared times vt. This is treated as the integrand and this multiplied by dt. This entire expression is denoted by, say, q of mu and y curl. Now observe that the first order partial derivative of the function q with respect to mu gives summation I from 1 to n del mu of integration yi to mu yi minus t by sigma squared times vt times dt, and that is equal to summation I from 1 to n yi minus mu divided by sigma squared times v mu, and that is nothing but our score function u. So this implies the function q of mu y curl behaves just like a log likelihood function. This is because the first order derivative of log likelihood function small l with respect to mu gives the score function, and here the first order derivative of the function q with respect to mu gives the function u, which is an analogy of score function del mu of L. So, in a true sense of term, the function q of mu y curl can be considered as an analogy of log likelihood function. We call u the quasi-score function and q the quasi-likelihood function, or more particularly the log quasi-likelihood function, because it actually resembles to the log likelihood function. These two, that is quasi-score function and quasi-log likelihood function, are the elegant instruments for executing the likelihood method under lack of sufficient information regarding the population probability model. Now, to describe how these two functions work, we can consider the next illustration. Let us consider an illustration. Let sigma is equal to 1 and v mu function is given as mu times 1 minus mu provided 0 less than mu less than 1. Then, from definition, our quasi-log likelihood function q of mu y curl is equal to summation I from 1 to n integration of yi to mu yi minus t by t times 1 minus t whole multiplied by dt. And on simplification, this is equal to summation of yi times integration dt by t into 1 minus t minus integration dt by 1 minus t, where the range of integration is as mentioned, and that is equal to summation of yi times integration dt by t plus dt by 1 minus t plus log of 1 minus t with value under mu and under yi. On simplification, this becomes equal to log of mu by 1 minus mu times summation I from 1 to n yi minus summation I from 1 to n yi times log of yi by 1 minus yi plus n times log of 1 minus mu minus summation I from 1 to n log of 1 minus yi. So this is what the quasi-likelihood is under the given choice of v mu. Similarly, we can get the function u, that is the score function here, and then with the usual method of likelihood, we can equate it to 0 and we can solve this equation either explicitly or with the successive iteration method to solve the value of mu, and that solution gives you the quasi-likelihood estimate of mu. In this module, we have gone through the similarity between score function and quasi-score function with respect to their characteristics in the light of exponential dispersion family. We studied here what the quasi-likelihood function is and its necessity under the shortage of information. We also explained through illustration that how this method works in scarcity of the probability distributional model.